Yeah, so the strategy for the optics is different from that of the anatomy. As you know, the anatomy is all about just remembering the facts. You read a piece of information and you just try to visualize it and try to imagine the relations, the and memorize. It is a basic solid memorization, but it is different, or it is total different story in case of the optics. You need to understand, you have to have a very firm understanding of the optical facts, and this is what we are trying to do in our course, and in either in the recorded lectures. So I'm trying to explain as much as I can of every details about the optic topics, and also we will try to more illustrate in the questions, and explain it very well so that you can understand. So let's start with the first question. Read the question and let me tell me what do you think the answer is. anyone anyone else want to participate? No other answers? Oh, this is a bit disappointing. This is an easy question. Yeah, that's right. It is the anti-reflecting coating. So can you tell me what is the difference in wavelength between the incident light and reflected light in case of anti-reflecting coating for in order for the interference to occur? And what is the type of interference? So Dr. Sadia saying it is a quarter. As we mentioned in the lecture, it is the thickness. It will be the difference between the wavelength in the incident and the reflected light will be half of the wavelength of the light in order for destructive interference to occur. As the light has to pass through half of the length or half of the wavelength, then the thickness of the anti-reflecting coating should be quarter. Yeah, that's right. So I'm talking about this cycle. I'm talking about the cycle. So it is half a cycle, but the thickness, it is the thickness of the anti-reflecting coat, which is just only one quarter. So this is the base of the anti-reflect, or the anti-reflecting coating is based on the on the base of destructive interference. So here, when we have the incident light is falling on the lens, it will encounter the anti-reflecting coat. As it will pass through the anti-reflecting coat, it will pass as it goes incident and emergent. So the incident light ray and the emergent light ray will cancel each other by the destructive interference, as long as the difference in the cycle between both of them is half a cycle. Okay, so let's move to the next question. Okay, let me give you a clue. Is the diffraction of light will be limited by small pupil, meaning that will the diffraction decrease by a small pupil? do you think that the diffraction will be decreasing by a small pupil? So the smaller the pupil, the smaller the diffraction? Exactly. Actually, the smaller the pupil, the more the diffraction. So it is not limited by a small pupil. So would you like to think of another answer? Here is another trick. Do you think that the a small pupil will be, or like for example, if there is a small pupil causing diffraction or any small aperture causing diffraction, is there any kind of refraction in this condition? Like any case of convergence or divergence, any case of vergence, will the pathway of light, is it changing? So there is no refraction. In the diffraction, there is no refraction. Please bear this in your mind. We are not putting convex or minus or concave lenses in front of the pathway of light, so it causes convergence or divergence. So there is no vergence here. So yes, let me bring my beautiful pen. Yes, that's right. It is producing interference fringes. So it is best explained by the wave theory, as there are the smaller the wave or the wavelength will affect the diffraction. So the larger the wavelength, the larger the diffraction. And also it's affected by the aperture. So the smaller the aperture, the more the diffraction. That's why it is not occurring by it is not limited by the small pupil. It is increasing by small pupil actually. And it is again, there is no refraction in case of diffraction, and it is just to produce interference fringes. As you can see here in this illustration, there is constructive and destructive interference that occur when the light or the emergent light from the both apertures meet each other, leading to forming of this interference pattern. So please read the question very carefully, because it needs only a single word to make the option wrong. Dr. Nihal, can you tell me why do you think that D is the right answer? Well, actually, it is, yes, it is D. D is the right answer. Polarizing a medium or the light polarization doesn't affect the spectral composition of light or the brightness or it is not a part of contrast sensitivity assessment. We will talk about the contrast sensitivity in the physiology, and we'll talk about the different tests for its assessment. None of them is polarization of light. And according to Elkington, the polarization of light can occur when light is reflected from the plane mirror. This sentence is typically extracted from Elkington book. I quote this paragraph from Elkington. According to the polarized light, a polarizing medium will reduce the radiant intensity, so it will decrease the intensity of light, but does not affect the spectral composition. And light is polarized on reflection from the plane surface. This is as per Elkington. So doesn't affect the spectral composition, and it will decrease the intensity of light rather than increasing the brightness. And also it is not a part of contrast assessment functions. And as you can see here, the light is polarized on reflection from a plane surface. Okay, so this is like a straightforward from the book. Let's move to the next question. Exactly. So it is, excuse me, what? C? Again, think again. Let me give you a clue. The pinhole, it is a small aperture or a small opening in front of the eye. Is it a lens? Is it a convex lens that will focus the light on the retina? Does it cause any vergence? So let me show you or draw you the difference. When we have a plus lens like this, the parallel incident light rays will come to a focus, which can be, for example, on the fovea. But in case of pinhole, there will be a barrier with a small opening. So this small opening or this barrier will block the peripheral rays and allowing only the central light rays to fall on the retina. Although in both conditions, the light is falling on the retina, but the mechanism of the pathway of light is different. There is vergence, there is focusing, there is convergence, but in pinhole, there is no vergence, as I just mentioned in the previous question. So it does not focus the light on the retina. This is a wrong answer. The optimum size 3.2. Again, this is a wrong answer. This is less than this, less than 2.5. And it can be used to test optic nerve function. This is again wrong. It can be used to test the macular functions, because if someone has a good visual acuity and we put a pinhole in front of him, this will allow only the central pencil of light to reach the macula. And if he has a macular pathology, the pinhole will worsen the visual acuity. And it can induce diffraction, and this is the correct answer. And we mentioned this in the lecture. I hope now that this is clear. Let's move to the next one. Yes, your answers are right. It is C. The range of visible light lies approximately between 400 nanometer and 780 nanometer. So let's discover why other options are wrong. A fluorescent substance will normally emit a longer wavelength when stimulated by shorter wavelength. So we stimulate with a shorter wavelength. for example, the blue light, and it emits a longer wavelength, for example, the yellow-green light. The cornea and the sclera will normally absorb the ultraviolet rays B and C, not A and B, it is B and C. And the absorption of this ultraviolet rays will result in this phenomenon which is called the photokeratitis or photophthalmia, which occurs to welders due to exposure of the ultraviolet rays. Also, the cornea and sclera can absorb the ultraviolet ray, the infrared rays C and B as well. So, and as you can see here from the spectrum, as we go from backward to forward from in the alphabetical, there will be increasing in the wavelength. So A is more in the wavelength than B, B is more in the wavelength than C. Again, here A is more than B and B is more than C. And finally, the lens absorbs the ultraviolet A, which will result in one of the pathogenesis mechanisms for development of cataract. And retina also can absorb the ultraviolet and infrared rays. So retina has a tendency to absorb the ultraviolet A and absorb the infrared rays, resulting in this appearance of 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 solar maculopathy due to exposure to infrared rays, like in the case of sun eclipse. This can result in macular burn or solar maculopathy. So let's get back to the question. A fluorescent substance emits light of longer wavelength when it is stimulated by light of shorter wavelength. Cornea and sclera absorb mostly the ultraviolet A, ultraviolet B, and C. The range of visible light between 400 nanometer and 780 nanometer, that's right. Ultraviolet A has a longer wavelength than the ultraviolet B. So this question has some topics that we didn't discuss yet, but I just brought the question because it's asking about the electromagnetic waves, and I will repeat the question again when we study the other topics. But just give me a wild guess. What do you think the right answer? Exactly, as we just mentioned, that the retinal photoreceptors are sensitive to ultraviolet A rays. This is the correct answer. I will just go quickly, very quickly through the other options until we study them in the relevant topics. Infrared is used in ophthalmic laser as aiming beam. This is not true, as you can see here. Just hold on, I think that the video is not working. Okay, just hold on for a second, please. Okay, I've just fixed it. So the sometimes when you can see a doctor or performing a procedure called YAG laser capsulotomy, you can find that you are aiming the beam or you are doing a capsulotomy or the removing of the posterior capsular opacification through a red laser. But is this red laser is the infrared laser that is removing the posterior opacification? The answer is no, because this is just what's called the aiming beam. The aiming beam is formed of the helium laser. This is the aiming beam, but the infrared beams itself are invisible. So the infrared are not red. So it is the helium laser, which is used in the ophthalmic laser as an aiming beam. So the first one is wrong. Retinal photoreceptors are sensitive to ultraviolet rays as A, which is right. Refraction of eye to infrared is approximately 1 diopter more myopic than the yellow-green light. We will say that this in the spherical aberrations and in the human optics, that the infrared rays are focused behind the eye, so the eye is more hypermetropic to the infrared light rays. Infrared rays rather than the ultraviolet rays, which are used in some autorefractometers in order to overcome the accommodation. So it is not ultraviolet. And here it is, the eye is hypermetropic. And here the infrared laser is not use an aiming beam as it is invisible. Here is the retina. As we mentioned, it is sensitive to ultraviolet rays A. And here is the red light. The red light or the infrared rays will be focused behind the retina, so it is the eye is hypermetropic to it. And this is the autorefractometer, will show the infrared light is the one which is used in some autorefractometer to avoid the use of accommodation. Okay, so regarding the photometry, which is right, we know that the human retina is not equally sensitive to all wavelength of light. That we just illustrated. The illumination of a surface defines its intensity as a stimulus. Well, here is the problem of a surface, because in photometry we can classify them into two big categories: the photometric measures. Some photometric measures will describe the source of light. So they describe the amount of light energy emitted from this source of light. And there is another terms that describe the light reflected on the surface. So they are not meant to, or they are not measuring the light that are coming from the source, but they are measuring the light which is reflected from the surface. The light intensity or the light power or the light flux, this is coming from the source, not reflected from the surface, as illumination from the surface is the luminance and the illuminance. Luminance and the illuminance are, it is the measuring the illumination coming from a surface. And the luminance specifically of a surface is measured by candela per square meter. This is the correct answer. While the lux is the measurement of illumination from light source, this is not true, as we will see here. But just let's read this question as well. It is the same options, but with just a single different answer. And then we will explain both. No, the lux is the illuminance. Lux is the unit of measurement of illuminance, and the illuminance is the light reflected from a surface, not coming from a light source. Okay, this is the same answer like the previous question, that it is the candela per square meter is the standard international unit for illuminance. Let's revise it again. The radiant flux and the radiant intensity, the luminous flux and the luminous intensity are measuring the light rays from coming from a source, or the energy or the intensity from a source. On the other hand, radiance, luminance, luminance are measuring the light or light energy reflected on a surface. So we are measuring how much the surface is perceiving light. In case of luminous flux, this is the light intensity or light energy. This is measured by the lumen. While the luminous intensity, in which it is the luminous flux at specific angle or stereo, this is measured by candela. When we are trying to measure the light intensity over the surface, we use the illuminance, which is the lux. It is equal lumen per meter square. As you can see here, we are now using a measurement for the space, or sorry, measurement for the surface. It is the meter square. So illuminance, how much intensity of light or how much luminous flux per meter square over the surface. This is the illuminance. So the lux, as you can see here from the question, lux is not an illumination from light source. As you can see here, lux is not an illumination from light source, because illumination of light source, it is termed luminous flux. But the lux is the measurement of illuminance of a surface. While on the other hand, the luminance without IL, it is measured by candela per meter square. Candela, which is the luminous intensity per meter square, this is called the luminance. So according to the question, the candela per meter square is the luminance. Again, the luminance of a surface is measured by candela per square meter. Is it clear now? Okay, that's right. Let's move to the next question. Okay, so the correct answer is that it is a virtual, upright, magnified, and behind the cornea. So according to the Purkinje-Sanson image, the first image or the first corneal image, it is called the Purkinje-Sanson image type 1. And this the first one or the first Purkinje-Sanson image 1 and 2 and 3 present at the anterior corneal surface, posterior corneal surface, and the anterior lens surface are all erect and virtual images because they are formed by convex surface. On the other hand, that one at the posterior lens surface, it is real and inverted because it's formed by a convex reflecting surface. And the anterior corneal surface, as we will discuss, as we mentioned before in the convex mirror, the image is formed inside the F or inside the focus. This is a virtual magnified and erect image, so it will be inside the F. It will be not in front of the cornea and not at the anterior surface of the cornea, but it will be behind the anterior corneal surface. So consider this is the anterior corneal surface, so the image will be formed here. And this will be the principle of a device that we will mention in the instruments. It is called the keratometer. So we have another question about the keratometer, or another question about the Purkinje-Sanson image. It has some other options, but again, it will be this principle will be discussed in more details in the keratometry lesson. So for this question, the first Purkinje-Sanson image, which is the image reflected by the anterior corneal surface, it appears behind the cornea, but it is not 6 millimeters. As we will mention in the keratometry principle, it will be only 4 millimeter behind the cornea. This is the object, and will be the image. It is a tapetal reflex. Tapetal reflex, it is formed by a layer in the retina called the tapetum lucidum, which will be giving like this shiny appearance of the eye. But actually, it is not in human. This is what is called by the tapetal reflex. It is what makes the eyes of cats and dogs appears shiny and bright. This is because they have a layer in their retina called the tapetum lucidum. We don't have this. It is an inverted image. No, we said it is an erect and virtual and magnified image and used to measure the anterior corneal surface because this is the base of a device called the keratometry to measure the anterior corneal curvature. So let's move to now again another question about the Purkinje-Sanson images. So you see that they love this topic in the exam. Are you sure? I have just said that in the previous questions. I mentioned that the posterior surface of the crystalline lens is the only exception because it is a concave mirror effect giving a real image, not a virtual image. Exactly. So we just mentioned that the anterior corneal curvature will be used for measurement of the keratometry or the K readings. Image from the anterior surface of the crystalline lens become larger during accommodation. This is not true. Actually, what happens in the crystalline lens during accommodation, that the posterior surface will bulge rather than the anterior surface. So the image from the posterior surface of the crystalline lens is erect. This is not true. It is real and inverted because it is formed by concave mirror effect. Image from the posterior surface of the crystalline lens is virtual. Again, this is not true. It is a erect and real image. So again, image 4 formed by the posterior lens surface is a real and inverted image because it is formed by a concave reflecting surface. The option A, the anterior corneal curvature, correlates to the corneal curvature or keratometric. It is said here it is keratometric. So if it is only saying that the refractive index of the cornea, I would say it wrong. But here it is mentioning it is a keratometric measurement. If it is not without this word, I will mark it wrong. Okay, another question. Exactly. So it results in magnified image, not a magnified image. The light rays become divergent after reflection. This is right. Focal length is half of radius of curvature, or the radius of curvature is twice the focal length, and the image is erect. Let's see here. This is the reflection caused by the convex surface. The image will be virtual, will be erect, will be diminished, and will be inside the F. This is very, very important. The characters of the reflection by convex mirror are very important and frequently asked. Yes, it is that's right. It's D. So the total internal reflection will prevent the visualization of the anterior chamber structure's angle, as we know. It occurs when a ray of light travels from optically more dense to an optically less dense medium. It occurs when the incident angle is more than the critical angle, and the critical angle is determined by the refractive indices of the media involved. This is correct answer. So we mentioned that the critical angle occurs when the incident light fall on the interface between the more dense to less dense at an angle which exceeds the critical angle, so that there will be total internal reflection rather than a refraction of light. So a critical angle is the angle of incidence of light ray passing from dense to less dense medium at which the emergent rays at 90 degrees to normal. If the angle of incidence exceeds the critical angle, then this will result in total internal reflection. The amount of reflection or the amount of critical angle will be determined by the refractive indices of the more dense and less dense medium. This is according to the Snell's law. So the Snell's law states that the refractive index multiplied by the sine of angle of incidence will be equal to the refractive index of the second medium multiplied by the sine of angle of reflection. So the sine, if one of the medium is air, then the sine of the critical angle will be equal 1 divided by the refractive index of the more dense medium. Again, a question about the total internal reflection. So as you can see, again, this is one of the preferred topics in the exam. Exactly. That's the principle of total internal reflection will contribute to the inability of visualization of angle without a gonioscope, as we use the gonioscope, we're making the light passing from the less dense to more dense medium so that it will undergo refraction rather than the total internal reflection. So do you think that the Paretos position will produce less deviation than the position of angle of minimum deviation? It is called angle of minimum deviation for a reason. Dr. Siddharth, why would you think that the deviation will be half of the angle of the prism if a small angle prism? And what is your definition for a small angle prism? What is the value of this small angle? Okay, so you all answered the all wrong answers except the right answer. This is funny, actually. Okay, the Prentice position is a position of the prism held in front of the face at specific position. What is this specific position? That the face near the eye, or the side of the prism near the eye, which is facing the eye, is perpendicular to the visual axis or the line of sight. As you can see here, this is the Prentice position. You can see that the side of the prism which is facing the eye has perpendicular relation to the visual axis or the sight, the visual sight or the axis of sight. And this means that the angle here is 90 degree. This is not equal to the angle of emergence. The angle of incidence, or the angle of incidence, like maybe acute angle, but the angle of emergence will be 90 degrees. So this means that the angles of both sides are not equal. So when you are flipping the prism on the other side, again, it will be the side facing the eye will be 90 degrees and the other side will be different. That's what makes this answer wrong. It doesn't produce equal deviations at two refracting prism surface. This can happen in the position of angle of minimum deviation. Here you can see this angle will be equal to this angle. This is the position of angle of minimum deviation, which will be the minimum angle of deviation that can happen at any position of the prism. It will be less than the Prentice position and will be less than any position. And it is understandable because it is called the minimum angle deviation. So in minimum angle of deviation, the angle of incidence will be equal to angle of emergence. This is the position of the prism. This is unlike the Prentice position. That's why in the Prentice position, a small error can produce a larger deviation. Unlike that, what's happening to produce deviation of half of the angle of the prism if a small angle prism is used, this is incorrect and inaccurate. And doesn't produce equal, we said that this is wrong. And the position of minimum angle of deviation will produce less deviation than that of Prentice position. So all these answers are present in the lectures. I hope that you study the lectures again. Okay, let's return back to basics. When we have a prism placed in front of the eye can see an object through this prism. Light rays from the object will be deviated toward the base. Again, light rays are deviated toward the base, but the eye and the image, both of them will be deviated toward the apex. So please pay good attention to what is the question asking for. Is it asking for where is the light rays are deviated? Always the light rays will be deviated toward the base. Or it's asking where is the image displaced or where is the eye moving. The eye and the image are moving toward the apex. I hope that this concept is clear because this is a crucial concept in optics. So image is formed by a prism is displaced toward the apex of the prism, not the base. The image formed by the prism is erect and virtual, as we can see here. The image is virtual. When prescribing the prism, the orientation of the prism is described by the position of the base. So we say base up, base down, base temporal, or base nasal. So you can say by exclusion that the first answer is correct, but let's understand, it will be a little bit difficult, but let's understand why in the hypertropia of the right eye could be managed by a base up prism in front of the left eye. So let's see that this is a hypertropia of the right eye. You can see that the right eye is a little bit elevated than the left eye, so that the right eye will show or will see a downward displaced image. The left eye will see a normal image, but the right eye will see a downward displaced image. So how can we correct this? We put a prism in front of the right eye, and this prism will have the apex with the deviation or the base against the deviation. And what will be the result? As we mentioned, that the image will be displaced toward the apex. So this downward image will be displaced up. so that we can both eyes can see a normal image, or the both images of both eyes they can fuse together, leading to no diplopia. So we put a prism base down or apex up, let's say that is base down, so that the image which is displaced downward will elevate up. But again, what happens if the amount of deviation is very much or very large? So one single prism in front of the right eye is not enough to bring the image up. So the other option is to bring the image of the other eye down. How is that? This is by placing a prism base up in front of the left eye. So by placing a prism base up in front of the left eye, this will result in that the image will shift down, as you can see, because the apex is down, and we said that the image is shifting with the apex, and the eye itself will be shifting down. So by putting both prisms in front of the eye, the base down in front of the hypertropic eye and the base up in front of the other eye, we can manage the problem by dividing the error of dividing in the deviation in both eyes, so that both eyes can see a fused image. Both eyes can able to fuse the images of both sides and not experience any diplopia. The same thing occur with the horizontal deviation. Let's say, for example, that the eye is exodeviated or deviated outward. This means that this eye will show a nasal shift of the image. This eye, instead of seeing in front of it, it will show deviation of this nasal image. So how can we treat? Again, we put an prism, the apex with the deviation, or base against deviation. So we put a prism base in, or the apex out, in order to try to shift this nasal image temporarily, so that we can alleviate this diplopia. But again, what happens if the deviation is more than the amount of the prism? Like, for example, if we have 90 prism diopters of deviation, and we have is a prism 45 prism diopter, so we placed it base in, and we want to shift the image so we can work on the other eye. We need to place a prism on the other eye that shift the image again toward the right eye. So what can we do? We put a prism base in again. This prism base in will cause displacement of the eye and the image toward the apex. So this nasal shifted image, which is present here, will be shifted toward the apex, leading to that both eyes can see the same image without any diplopia. So if you see, this is the base in, we do base in prisms in case of exotropia, and base out in case of esotropia for both eyes. This is the way how can we divide the deviation on both eyes in case of that the error is very much or very large, so that the patient will not wear one prism in one eye, and it will be ugly to have only one eye with a prism. So we just divide the deviation on both eyes. I hope that it is clear now. So don't confuse one of the common mistakes in these types of questions, to confuse between lenses and mirrors. Focus, what is the question is asking for? It's asking about lenses, not mirrors. So concave mirror can cause a real image, but concave lenses can cause virtual image. So this is wrong. Concave lens may be detected by moving an image in the same direction of lens. This will be the true answer. As we mentioned before, the power of the lens is perpendicular to the meridian of the axis. We said before that the meridian of its axis has no power, and the perpendicular meridian will be having the power of the cylinder. The power of lens is divided in diopters will be divided or defined as one divided by the focal length in meters, not in centimeters. So we said before that image construction by the concave lenses, it will be a small image. This small image is a virtual image. And in concave lens, if we are moving the lens in front of a cross, this will result in movement of the cross in the same direction of the movement of the lens. We said also that the cylindrical lens has no power along its axis as it acts as a plate of glass, and the maximum power is 90 degrees from the axis or perpendicular to the axis, whether it is concave or convex. And we said that also that the basic definition of power of the lens is the reciprocal of the focal length. And the reciprocal of the focal length is expressed in meters, not in centimeters. So is it clear? Does anyone have any confusion?
No, sir.
Please stop me if you have any question or you have any confusion. Okay, let me explain this to you. A sixth nerve palsy patient will lead to the paralysis of lateral rectus, leading to esotropia. So this patient with esotropia now has his both eyes are not aligned. They are horizontally displaced. So they will see two images 24 centimeters apart at 6 meters. What is the angle of squint? The right answer is 4, but let's say why it's 4. We know that a one prism diopter will move the image 1 unit at a distance of 1 meter. So let me draw you an illustration. Let's see that this is an object. Let's see, for example, that this is a flower. Consider it as a flower. And we have here a prism. So what happens is that this flower image, the light rays will cause deviation toward the base. So when the eye looks at this flower, the light or the eye will show the or will see that this flower at the extension of light rays. As we mentioned before, that the eye cannot see in broken lines. It needs to see in a straight line. So it will see an image for the flower. This image is virtual, erect, and displaced toward the apex. So how much displacement? It will be displaced 1 centimeter if the image or if the object is placed at 1 meter from the prism. So again, a prism diopter moves the image 1 unit at a distance of 100 units. So that if we have one prism diopter, will move the image 1 centimeter here at a distance of 100 centimeters. So what happens if this 100 centimeters or this 1 meter become 6 meters? Then a one prism diopter will move the image 6 centimeters if it is placed or if the image or if the object is placed at around 6 meters. Again, if this distance is 6 meters, here from here to here it is 6 meters, this will result in movement displacement of this image for a 6 centimeters. And what happens if we are using a 4 prism diopters at a distance of 6 meters? So this will result in multiply 6 by 4, it will be 24 centimeters. So the right answer is a 4 prism diopters will displace two images 24 centimeters if they are placed at 6 meters away. I hope now that you understand the concept or how we calculate it. So nobody is answering me or telling me if it is understandable or not. I don't know if this is good news or bad news. If
It's okay, sir.
everything clear or it is still vague.
No, it's clear.
Okay. Another question about the cylindrical lens. Okay, so the Maddox rod is comprising of a row of powerful convex cylindrical lenses, not cylindrical lens. A toric lens will produce a line foci, two line foci, they will be perpendicular to each other. The axis of the cylindrical lens is the meridian, which has no Vergence power. We mentioned before that this is the correct answer. And the line image of a point object formed by the cylindrical lens is perpendicular to the axis of the lens. So no, we said that the image or the image is formed by the point. If we have a point object and we are viewing it through a cylindrical lens, this cylindrical lens will make a line image of this point object. This line image will be parallel to the axis of the lens. So don't confuse between the power and the axis. The image is parallel to the axis, and the axis has no power. Let's see this in more illustration. We mentioned before that the Maddox rod has a convex lens. As you can see here, this Maddox is oriented vertically, and it will result in a horizontal line. This is because it is formed of powerful convex cylinders, and we know that the convex cylinders are forming an image perpendicular to its meridian. Here the circle of least this is the toric lens, and you can see that the toric lens is forming two line foci. This is the first one, and this is the second one. They are horizontally, they are perpendicular to each other. The cylinder, as we mentioned, has no power along its vertical along its axis, and the maximum power will be at 90 degrees from its axis. Let's see this illustration will summarize it all. So we have here a pointed object. This pointed object will project light rays that will come to the curved surface of the cylindrical lens. Each plane of the curved surface will form a point of focus. So here, this will lead to a point of focus here, and this surface will act as a convex mirror, convex lens, making a focus here, and this surface will make a convex here, point here. So if we are joining now all these lines of foci, this will result in a vertical line. This line is parallel, this focal line is parallel to the axis of the cylinder. You remember this axis which has no power, and the power is on the perpendicular meridian. Again, the image is parallel to this focal line. So focal line is parallel to the axis. Another question about the Maddox rod. Exactly as you mentioned. As we mentioned, it is consisting of powerful red convex cylinder lens mounted side by side. Light from the far spotlight is deviated by the lenses in case of Maddox rod. So Maddox rod is used for far light or far object. On the other hand, the Maddox wing, which is the one used for the near objects. Cylindrical lens within the Maddox rod refract parallel light rays to come to a focus at the retina, not anterior to the globe. As you can see here, this is just contradicted by the second one. It is, say, the linear retinal image, so it is focused on the retina, not anterior to the globe. The linear retinal image of the distant spotlight viewed through the Maddox rod is perpendicular to the axis. This is correct. So this means that if we are placing the Maddox rod vertically, actually what we see is a horizontal line. And on the other hand, if we are placing the Maddox rod horizontally, what we see is a vertical line like this, like this. So the retinal image is perpendicular to the axis. Here you can see this is what exactly of what we see if we are placing the Maddox rod in front of one eye, because Maddox rod is a dissociative eye test, making the right eye see a spot of light and the left eye will see a streak of light. If both are coinciding, then this means that this patient doesn't have any heterophoria and the eyes are orthophoric. They are aligned well. But if the light is displaced, or the vertical or the streak of light is displaced from the spot of light, then this means that this patient has heterophoria. Okay, let's move to the next question. Okay, to know or to understand the concept behind this question, you need to understand what is the concept behind the Fresnel prism. Actually, the Fresnel prism is just a cosmetic way to handle the prisms, meaning that instead of putting a single large prism in front of the eye, which will be ugly, then we can place a sheet of prisms. They are called Fresnel prisms in front of the eye. But actually, this is not only about cosmesis, but it's also about the flexibility. So Fresnel prism can be easily removed and changed, especially if the patient is needing prism for temporary reason or their angle of deviation are changing frequently. But permanent prism can be used for all the presbyope where they are not expected to recover, and they are expected that their angle of deviation will be fixed and permanent. So having said that, the refractive power is usually split between the two spectacle lenses. This is used for the conventional prisms, as I told you in this animation, the previous animation where we split the prismatic power in two eyes. This can be used for the conventional prisms to make them looks like the same and avoid any disparity in the image between both eyes. The same effect can be achieved by using a single large prism into the spectacle correction. This is correct because, as I mentioned, that the Fresnel prism is a way to just it will provide the same power or the same prismatic power like a conventional prism, but we are just making it is smaller and thinner. How does it do this? By having a parallel tiny prisms that have the identical refracting angle. They are not gradually increasing in the refracting angle, and they doesn't form or they don't contribute to the optics of applanation torometer, as we will mention in the instruments. So here is the Fresnel prism. The Fresnel prism this is the difference between the Fresnel prism and the conventional prism. So both of them will provide the same overall power. The same overall effect will be the same like Fresnel, the same like conventional, but they are just can be used to be adherent to the back of the glasses by like water, so they are flexible, easy to use, lightweight, cost effective. But one of the major disadvantages of them that since they are formed of multiple tiny small prisms, they will cause degradation of the visual acuity. They will cause decrease, causing glare. They will cause visual decline and chromatic aberrations. So they are not the best in terms of visual acuity. These are the pros and the cons of the Fresnel prism. Another question about the Fresnel prism. Exactly, as I just mentioned, that it is a lightweight, allowing to correct large angle deviation without using a very large prism that will be ugly. And they are attached to the spectacle usually with water, and they can be cleaned with detergent, and the small tiny prisms are of identical refracting angle. Okay, we come to questions about transposition, and this is a must in the exam. You will must find a question asking you to do a simple transposition of to change the cylindrical form and the power between both prescriptions. So can you tell me what is the cylindrical or what is the transposition of this prescription? Exactly as you mentioned. So how we do a transposition? We add the sphere to the cylinder to make the new sphere, and then we take the opposite sign of the cylinder. So if it is minus, it will be plus, or plus will be minus, and then we take the axis, complementary axis, or the perpendicular axis. So if it is 90, it will be 180. Another question about transposition. Exactly as you mentioned, the same concept of a spherical transposition. So I hope that you don't confuse this in the exam. It is a very simple and very guaranteed question in the exam. Exactly. So we still didn't take or didn't discuss the spherical aberrations. So you will find it in the second week lectures, but it has no relation to reduce spherical aberrations. It is can cause spectacle intolerance because of the prismatic effect that result from decentration of lenses, leading to intolerance to spectacles, especially if there is high power. So the higher the power of the lens, the more the decentration, leading to more intolerance. The prismatic effect can be calculated by multiplying the lens power by decentration in millimeters. What makes this option wrong? It is millimeters, because it is multiplied, or the Prentice rule is calculated by multiplying the lens power by the decentration in centimeters. So please take care of this. The lens decentration, or the prismatic power, equals lens power multiplied by decentration power. The lens power will be in prism diopters. The lens power will equal F, which will be in diopters. H is the decentration, will be in centimeters. Exactly, as you mentioned. So we said during the lens verification that if the lens is rotated, which is cylindrical lens, there will be a scissoring effect of the cross. So here is, if we place this cylindrical lens over this cross, this will result in scissoring on rotation due to unequal movement of the vertical and the horizontal line. So this will result in distortion of the cross, as you can see. This is the final question. Exactly. So it will be what happens if we put a base in prism in front of, or what happens if we put a concave lens in front of the eye and shifting it nasally? Let's see. Here is the eye and here is the lens causing nasal shift, or what we do is nasal shift toward the nose. And now what happens? Instead of that, the center of the lens is in front of the eye. Now there is a prism in front of the left eye. This prism has apex in and base out. So decentration inward toward the nose of a minus lens will result in a base out effect. So the first one here is wrong. A base in prism will be induced by a base out prism will be induced by horizontal displacement or horizontal decentration of a concave lens nasally. A prism of one prism diopter will give apparent displacement of 1 centimeter to object at 10 centimeters away. No, it will give 1 centimeter displacement of an object placed at 1 meter away. As you can see here, the object is placed at 1 meter, resulting in displacement of 1 centimeters. An object view through the prism is always deviated toward the base. We mentioned before that the light rays is deviated toward the base, but the image and the eye are deviated toward the apex. So when you are seeing an object through the prism, you will see the image deviated toward the apex. A prism are placed base in to relieve exophoria. The relieving prism are always constructed so that the base will be against deviation. So if there is, here you can see that the eye is deviated toward the apex to see the apex, and the relieving prism for case of exo or iso or hypo, this will result in or will be a deviation toward the against deviation. So this is the deviation, the base against deviation. So here is the deviation where the deviation is outward or temporal or outside. So the base will be in. So this is the end of our lecture. I hope that you enjoyed it, and I know that the optics is a little bit tricky and needs good understanding and needs to watch the lectures more and more. Optics are never can be grasped by just single reading or single view of lectures. You need to watch them again and again and try to solve as much questions as possible in order to grasp the question's ideas and to know how to think. As you can see that the optics is like math. It is like mathematical equations. You just put some input to give you output. It is a total different strategy from studying anatomy. And by today's lecture, I think that you are now able to figure out how do the questions look like and how to think about it. Do you have any question in today's lecture?
No, sir.
Uh, Doctor, can you hear me, Dr. Ahmed?
I see that there are some of you are talking, but I can't hear anything. Please tell me in the chat box if anyone needs anything. I don't know why I am not able to hear you. Okay, do you have any question? It is based on a curve. So the pass in the exam is based on the curve. So this is a good thing because it will be, the curve will be variable according to the difficulty of the exam. Usually the pass rate is around 60 to 62%. It is a percentage depending on the marks or depending on a curve. So after they put the exam, they just make a curve of what is the results and take an average. And above this average, people pass, and below this average, people don't pass. Okay, thank you very much, and I hope that you will be ready for the next Friday exam of the anatomy. Please study hard, and also this shouldn't prevent you from studying optics in parallel. So you are preparing for the next class of human optics. I think that after today's lecture, things will become more interesting in the optics because human optics have some applications in the clinical life and are more interesting than the dull physical and geometrical optics. Okay, thank you very much for your attention, and good night.